we're keeping going this day with the Wkb program, and now we're going to have Frederic Fauvet from Strasbourg, and he's going to tell us about coequational resurgence and how we can apply that to do properly Wkb analysis.
Thank you very much. So, of course, I'm very grateful to the organizers of this ARA program for the possibility to attend this program, participate, and to the organizer of the workshop for the kind invitation to give a talk. As it's written, it's a joint, I'm reporting on some joint work with Shingo Kamimoto in the University of Hiroshima, and David Sauzin with the CNRS in Paris Observatory. And it's an ongoing work, and it's part also of a broader program with Ricardo's Kappa. And we have achieved one step. We have one more step to do. I'll explain this in a while, but we still think at this stage that we have something which is not uninteresting to report. So that's why I'm here today. So it's about resurgence. You will see some of Ekal's terminology and techniques, but I'll try to avoid the jargon as much as possible. Okay, so where we are, we revisit a very well-known problem. So I will be concerned with the stationary Schrödinger equation in one dimension with a polynomial coefficient. So the Q is it's a polynomial. It can possibly depend upon h bar, and we'll see that in the last part of the talk. And actually, there is one section of the last part of the talk which is devoted to some homogeneous potentials, and it's very recent part of our work, which was triggered by a paper published a few months ago by André Voros. It was dedicated to Professor Michael Berry, and when David Sauzin saw this paper, he immediately reacted, and we had something to say about some resurgence properties about Schrödinger equation with homogeneous potentials. So, but for most of the talk, Q will only depend on X. X is the dynamical variable. We don't call it Q here, we call it X. It fits with some recent terminology anyway. And I, from the start, draw your attention to the choice of the variable. Here, to study the resurgence properties, it's of course convenient to use a variable which is close to infinity. So here it's 1 over h bar, and we call it eta. So eta is large, close to infinity, and we are interested in the expansions in eta minus 1. So this type of objects. Okay, as well known, the solutions to these equations can be expanded by using this Wkb analysis. And there are exponential factors with an action a of x, and a part which is q to the 1/4 of x, and asymptotic expansion in eta minus 1 depending over x. And our results concerns the resurgence properties for the Borel transform with respect to this large variable eta, so with respect to the Planck constant. Okay. So this Schrödinger, let's think. Yes. Okay. So this Schrödinger equation can be solved by the Neumann series. I mean, we can write it as a two-dimensional system, and there are two components, phi denoted here phi plus and chi plus, which is the derivative of phi plus. And phi plus can be expanded in this way. And it appears as an infinite sum of functions, the n to the minus plus times n. It means there is a word of n times minus plus. Maybe you have seen in the abstract, I've spoken about words, expansions indexed by words in letters. The letters here will always be for us plus and minus. And we'll also see expansions indexed by trees in what follows. Okay, when we explicit this expansion, we immediately find this following recursion for these functions. So the functions we are interested in, once again, depend on eta. And there is the variable, the dynamical variables, which appears in the data b epsilon I. And this is sort of the most important equation for the rest of the talk. We'll see it in different guises. This recursive equation, m will stand for, like, there is this letter m, stand was mode. And I will tell a little bit, really a little bit of Eccles mode combinatorics, which is required for what we are doing. Okay. So the operator delta z plus eta is invertible in the space of formal series. So this is not a problem, but it's delicate when we go to the Borel space, because when you invert this operator in the Borel place, multiplications by eta correspond to the derivation with respect to psi, which is the Borel variable associated to eta. Okay, so our notations, eta in the Borel plane, we use the variable psi. So psi is the Borel variable which is associated to eta. And when the multiplication by eta corresponds by Borel transforms to d over d psi. So as most practitioners of Borel summation for Wkb expansions, more generally singular perturbation problems, know well, you have to solve a PDE in the Borel plane, which is much more difficult than analyzing the resurgence properties with respect to the variable z, which is connected to the dynamical initial variable x. When we have something like that here, the Borel transform of dz is multiplication by minus zeta. Here I use a zeta, it's a standard notation for the variable which is associated to z. So you see, once again, let me just write this relation here, because we'll, when you have something like that, so a word epsilon 1, epsilon r, remember the epsilon I are just plus or minus, and here you also a word, but of length r minus 1, you have erased the first letter. So in this recursive relation, at the formal level doesn't pose any problem, but in the Borel plane with respect to z, it's simple, because inverting this operator here in the left, on the left-hand side, amounts to dividing by minus zeta plus I eta. Okay, whereas in the Borel variable, which is associated to eta, you are dealing with partial derivative with respect to eta, and so you have to solve partial differential equation in the Borel plane, which is of course more complicated. So the problem, yes, yes. Sorry, I did not. Z is the action, is the variable. I've not given detail on that for the moment. You'll see it later. Z is the variable close to infinity, which is associated to the dynamical variable x from the start, and which is given actually by the action which was on the first slide. Let me.
Z is complexified x, is that right?
Z. Well, we take x, x is the complex dynamical variable here, and actually z is the action a of x. Okay, well, sorry about that. It should have been, I should have mentioned it from the start here. Is that clear now? Z is the action variable. It's directly related to the dynamical variable x this way, and we see it in the next stage in the recursive relation, which is this M equation. The derivation here, d, which appears here, is the d over dz. Okay, and that's why this equation in the Borel plane corresponding to z is rather simple, whereas what we are interested in, the transforming this equation in the Borel plane, which corresponds to eta, the inverse of the Planck constant, is something more complicated. So the questions we are addressing in this work is, are the expansions resurgent? Okay, we all know about André Voron's fantastic paper in 1983, when an incredible number of rich relations were found for these expansions, but one fact was conjectural, admittedly, André Voron is very precise about that, is that are the Borel transforms with respect to eta endlessly continuable? And I'll make that precise more precise in a while. So André Voron stated as a conjecture that the Borel transform of the expansions in psi had only isolated singularities. And from that, he derived a number of fascinating resurgence relations, which he named at the time analytic bootstrap. So the question we are addressing with David Sauzin and Shingo Kamimoto is the fact that indeed this expansion have Borel transform with isolated singularities. And it's delicate because we have to solve a PDE in the Borel plane. Okay, let me mention that Frederic was very well also aware of the problem and the difficulty of the problem. And in his last paper in '99, it was still quoted as conjectural. Actually, to be fair, and I will come back at the end, Ekal himself had produced a family of iterated integrals, which in principle solved the problems, but the calculations were never performed in detail. That's why we had room to perform our work. Okay, I'm convinced that Ekal's integrals are very interesting objects, and eventually someone can certainly make a precise calculation along these lines, but they had not really been made until now. That's why we wanted to address these problems, and we have also other outlooks in perspective. Okay, are there other questions? Thank you.
You will explain the relation with the old resurgence of Dingle.
Yes, actually, well,
in the 60s.
Yeah, I know. Once again, I'm well aware that for the Dingle was certainly the first one to discover in the context of Borel transform or divergent series the phenomenon of resurgence. Ekal coined the word later on, but I'm well aware of this. And what Ekal did suddenly is go more further into nonlinear equations. That's what he needed. Well,
your context is linear.
Yeah, yes, here it's linear. Yeah, you're perfectly right. But after a while, we'll deal with Riccati, the associated Rickety equations, and there it's nonlinear. It's easy nonlinear, but still there it's easy, but it's not trivial. The resurgence properties for the solutions in the context of Riccati equations are not trivial. That's why we needed this this scheme which we implemented. Okay, and thank you again, Ines, for your question. Other questions or remarks? No? Okay. Yeah. Yeah, I have a U. It's a renormalized, and I was coming actually right, that's why I wanted to go back to this slide. It's a renormalized Liouville coordinate, because you see in the equation, which was the previous page, let me come back, it's better. Okay, there's this 2i. In order not to drag this 2i, we renormalize the thing, and U is Z divided by 2i. Sorry, okay. And so later on in the formulas, we'll see the derivative with respect to U, which is the Liouville coordinate divided by 2i, which makes life simpler later on. Okay, and so I wanted to go back to this slide. Inverting this operator in the Borel plane, in the psi plane, the one which corresponds to eta, if the right hand, when we want to invert this operator, in the right hand, if in the right hand side we have just a function which depends only on U, it's simple. It amounts to a translation. It's the exponential of psi d over du, so it amounts to a translation. But of course, if the right-hand side depends on the two variables, u, directly connected to the dynamical ones, and eta, then it's more complicated, but we have some integral formula taking into account the standard limit conditions. Okay, and so we have to work for with an iteration of this kind of formula. And when you do this thing, you don't have an immediate access to the singularity in the Borel plane. Of course, for summability, it's okay. Many people have dealt in various contexts with questions of summability. You take a direction where you don't have singularity and you solve the functional equation in some suitable space of analytic functions in the Borel plane, prove that you have exponential growth at infinity and that you get summability, and many interesting results have been published on these lines. What we want to do is we want to go around the singularities. We want to first thing to prove that indeed there are isolated singularities for the analytic continuations. And this is a question which was not, once again, far from trivial. It was considered still to be open by Frederic in 1999. Okay, very briefly, but just two pages on 2-3 pages on resurgence using a part of Ekal's terminology. So resurgence for a family of functions which have Borel transforms of some formal expansions, say. It means first that the functions are endlessly continuable with isolated singularities. Functions which have disk of convergence, which can continue with only isolated singularities, no natural boundary, for example. And second point is that at any singular points of any of these functions, the singularity is expressed by a combination of a family of some of the phi j. And this is the phenomenon of resurgence. When people in the applications, that there are so many in these recent years, speak about a resurgence, is the fact that we have some function in some Borel plane with respect to some variable which are interested in. We start from a divergent series, Borel transform, we continue it, and we see at the singularity a behavior that looks like with some other functions of a given family of functions which describe the problem, the total solution of the problem you are interested in this first. Okay, but there are two stages, and the first one is important. You can take for granted that you can continue with analytic singularities, with isolated analytic singularities, but it's better if you get a complete proof of this fact. So we just addressed the first point. Of course, it's part, as I said, it's part of a broader program in which we want to understand from Ekal's point of view and enrich what is known to this day, the resurgent properties of the functions at their singularities. But just the first stage. And the first stage is not yet completed. We have 2 steps, and we have just achieved for the moment the first step. Okay. So these are the 2 pages on resurgent functions, and with one very easy thing, and I apologize for the greatest part of the audience. This must seem, of course, too simple, but it's so important. But I prefer to remind this. Okay, so functions. When we speak of resurgent functions, we deal with functions which are convergent in a disk at the origin. Here, let's say the psi plane. And if we take any broken line, which can cross like this, you can analytically continue along this broken line, except that you can meet, even here, for example, a finite number of singular points, which you must be able to circumvent. Okay, so if you have a singularity here, you require that the analytic continuation is possible this way and that way. And in this, in doing this, you have an access to a description of this type of singularity you have at this point here, and then later on, and then later on. Okay, so this is functions of this type of structure of vector space, but there is, of course, the convolution, which for variable close to the origin, for when zeta is close to, here, denoted the variable zeta, close to the origin is given by this well-known formula. And the rule of thumb, and a very important thing, of course, is that convolution adds singularities. Generically, if you have a singularity at one point alpha and one point beta, if you perform the convolution, you will have a singularity at alpha plus beta. And it creates multi-valuedness. If you start with functions which are, say, meromorphic in the Borel plane, then the convolution will create functions which have multi-value, to introduce logarithms or ramification points. Okay, a basic example is that if you take just two single poles, the two points alpha and beta in the Borel plane, here you have an alpha, beta. So you expect a singularity here at alpha plus beta. But in fact, defining the function, the expression that defines the convolution shows that you can use it as to perform the analytic continuation along any straight lines, in particular along this line. What's wrong? What's wrong is the fact that in the first sheet, in the main sheet, in the star of holomorphy of the function in the Borel plane, there is no singularity. There will be one generically if you turn around here or if you turn around there. So when you start to work with equations in the Borel plane, you have to deal with this kind of questions, and it's immediately delicate. Of some practitioners of resurgence among you have, or of course, know, but maybe not everyone in the audience. Okay, so the point is that it's not only the fact that it's some direction we want to know that in maybe perhaps in some sheet we have a singularity. We want to address as precisely as possible the position of the singularities in the various sheets. And in the problems which were considered by André Voros at the start, he was well aware that these questions were delicate. You have a lot of multi-valuedness. The whole set of singularities for various potentials, most of the potentials would project on the Borel plane in a dense set, but they remain isolated when you perform the analytic continuations in the various sheets. So this is a delicate point, and this is why some technology is required to deal with these questions. Okay. This one is a big pact. Okay, it's just to remind that I started with regular germs at the origins to perform analytic continuations, but we can also deal with germs which are regular, which are defined at the origin of the Riemann surface of the logarithm. This way, you can deal from the start with a singular germ and require that it can be analytically continued along any broken line like that. And a general resurgent function is then a class modulo analytic function at the origin of a singular germ, which is endlessly continuable. So from the beginning, resurgent functions are not functions. They are classes and functions, but we can work with this. On an algebra of resurgent functions, there is a generalization of the formula of convolution defined before, and we get also this way algebras of resurgent functions. And on these algebras, we have families of operators which measure the singularities. As I said before, we can go around the singular points which we meet, and this way focus around one's given singular point and the singular behavior at this point, and define families of operators with this. And among them, there are the so-called alien derivations due to Ekal, and there are many families of alien derivations and which have precise use. Okay. Now, remember in the title of my talk, I referred to coequational resurgence. Coequational, the word was also coined by Ekal soon after Voros' fantastic discoveries to describe the situations where we have resurgence with respect to a variable which is a perturbation parameter. Okay, not a dynamical system, not a dynamical variable for some dynamical system. But from the start, Ekal started his theory by studying very difficult moduli problems for classification of complex analytic dynamical systems at irregular singularities with discrete or dynamical time. Actually, he started with discrete time. in the mid-70s. And the point is that these things are very important. The locus of the singularities in this case is rigid. It's essentially determined by the spectrum of the linear part of the dynamical systems you are studying. Whereas in coequational resurgence, it's much more flexible. You can have singularities all over the place, so to speak. Now, it's a fact. So that's why I was saying that it's phenomenological. In any situations where you classify dynamical systems, and so difference equations, differential equations, linear, nonlinear, even Q-difference equations, and you can have mixed difference and differential equations. Ekal has studied also that. The action of the alien derivation on the total space of formal solutions amounts to the actions of ordinary differential operators. So as many people among the audience already know, there is a bridge, that's Ekal's terminology, between alien and ordinary differential calculus. And the coefficients of these operators are transcendental constants, and they encode the Stokes data for the trans series, the total space of solution. Okay, I've finished with these generalities. Are there any questions? No? Okay, here again, very classical material. It's just the Riccati equations which are associated to Schrödinger equation. Of course, Schrödinger was linear. Here we move to, I don't give all the details, but it's very well known. So the Riccati equations, which I will normalize the first time like that, d on top of the slides, d is d over dz, and then at the bottom, remember your question, Ines, it's renormalized to in du. U is the renormalized Liouville constant. So there are two unique formal solutions to these equations. There are two Riccati equations, corresponding to two signs, plus or minus, and from which we can recover the formal solutions normalized at infinity. In our work, we normalize at infinity. It's more convenient. Of the Schrödinger equation. Okay, so we have a new way of writing a Schrödinger equation, and from there, we have the connection directly, the connection between the phi plus minus and the solution y plus of minus of the two Riccati equations. Okay, from the rest for the following slides, I will work now with the Riccati equations and prove and show how we deal with the problem of analytic continuations in the Borel plane with respect to eta of the solution of these Riccati equations. Okay, so now I will I must now say a few words about Ekal's mole co-mole formalism, but just the bare minimum. For the Riccati equations, we can define, and I'll tell in a second why it is natural, two operators, d over dy, and b minus, which is minus y squared d over dy. And you can take it as an ansatz. When I introduce these numbers, the beta plus epsilon 1, etc., epsilon r, so these are as before, plus or minus. The epsilon I are plus or minus, okay? Then the solution of y plus, there is a similar formula for the other Riccati equation, y minus. Y plus can be expressed as this sum. You see, it's a big sum. It's a sum over words, but the words are in two letters. So you sum over for every n, even number, for every, integer n, you consider families of numbers, finite of n numbers, let's say a word with the letters plus or minus, and you consider all these families. So it's an innumerable sum, and you can show that y plus can be expressed in this way with these numbers, which are explicit. And how do you define the numbers? You let the operators b plus or b minus, so you see, to compose them on just the variable y, and by the homogeneity properties of these operators, the homogeneity is of -1 or +1 respectively. And so it's a fact that when you let the operators B epsilon R, etc., B epsilon 1 act on Y, you get a number, which is a rational number. So there is no mystery in these numbers. They are just rational numbers. But the point is that Y plus is a solution of the Riccati equation, which was in the previous slide, if and only if the coefficients satisfy the equation MX, the mold equation, which we had before. So you see, there is something quite striking here. You had an equation for the Schrödinger equation. We had expanded this using the Neumann series, which is standard, of course, a very standard thing. As an expansion over words, we have something similar with the very same equation for the Riccati equation. And in fact, what is behind is that there are some symmetry properties, which is called symmetrality, for these coefficients, which explain this striking fact. So solving the Riccati equation, and what we have in mind, once again, is proving the endless continuability property, no more for the moment. Afterwards, we would like to understand better, of course, the coefficient, the Stokes constant expressed in through this combinatorics, but we're not here for the moment. We want to prove endless continuability. So we have a formal expansion, explicit, and we then perform the Borel transform and show that we have endless continuability. Okay, let me check. Fine, good. One thing about these objects, why do I introduce these operators out of nowhere? It's just a very standard procedure. Ooh, this one is not so good. Ah. Yeah. 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 Okay. I use one of these. I didn't bring mine. Yeah, yeah, okay. Okay. It comes from normal form theory. When you have a dynamical system which you want to study, and once again, the procedure is very general. It can be a vector field with singularity. It can be, you might be interested in some fixed point of some diffeomorphism in any dimension. Let's say a vector field. You have a vector field with a singularity, and you have some normal form. Maybe it's linear part. In some cases, it's more complicated. You want to transform it. Let's say theta with a normalizing transformation. Okay, just a change of variable. And maybe this change of variable might be change of variable might be divergent in some variable, might be resurgent. That's the point. But this change of variable, we can express it as an automorphism. Let's say you are in dimension nu. Here f can be some formal series. It's an observable, so it's a formal series in new variables, or it can be a convergent germs, or it can have some intermediate regularity. There is this big operator here. So knowing the change of coordinates is equivalent to knowing this big thing. So this thing here lives in a much larger space than the space of changes of coordinates, but the equation you will have for the big theta are linear. And that's the thing that Eckhart does all the time in many contexts, and with great successes in the end. So now there is an ansatz. X is its normal form plus some perturbations. Imagine you're in Riccati, there are two terms. There's a normal form, there are two terms in the perturbation. One is of homogeneity minus one, of one of homogeneity plus one. In more general situations, you can have many more terms, but the process is the same. This is an ansatz. You look for a normalizing transformation in this way. And then you get, and these ones are just a compose of the elementary bricks you started from. I'm forced to be very, very, very brief, of course, here. Once again, dynamical system, it's a normal form plus a sum of perturbations. You take these bricks here, you compose them as like in the second line of the slide. This gives you operators, which are just composition in this case of ordinary derivations, which are indexed by words. And then you put in front of them coefficients which belong to some algebra, and you work on the equation satisfied by these coefficients. Very often what you obtain is very simple equations on these coefficients. So this guy here lives in a huge space, but you had replaced a nonlinear equation here by a family of linear equations in some bigger space. And you're able to explicitly solve these linear equations. That's a general philosophy. In this case, we take a little bit of this general method of Écale in the context of a Riccati equations. That's why a pair of Riccati equations. That's why we have these two letters. And with these two letters, we construct the product of operators, B epsilon I. It gives us numbers. And then that's why when we look for a solution of Riccati equation with this coefficient, we find a solution, an equation satisfied by this coefficient, which is simple and actually the same one that we had seen in the second slide for the Schrödinger equation. Now, what is the, okay, this thing, okay. What is the method to prove the endless continuability? So we expand the solution either for Schrödinger equations, as we have seen before, or for the Riccati equations by the sum of elementary components. Of course, it's an infinite sum. It's doubly indexed because you have the length of the sequence which are involved, and you have the letters in the sequence. You can have plus, minus, plus, or minus, minus, plus, etc. Then you show that the Borel transform of all the components are endlessly continuable. That's the first step. And then once you have proved this, when you have proved this, you have to show that the sum is convergent in a suitable space of resurgent functions. What we have achieved at this stage is the first step. We have proved that for coequational resurgence, corresponding to Wkb problems with polynomial potentials, all the components of this equation MX, mold equations, are indeed endlessly continuable. Okay. And once again, this thing was yet to be done. It's not a new proof, except once again there is Écale's explicit. No, let me come back. Yes. Integrals, which, as I said, which have never been worked in detail. Okay, so there is a recursion on the length of words of the size of trees. I'll come to trees in a minute. And we express the solution for the mold equations as some explicit iterated integrals, which are unambiguous for psi close to the origin. Remember the simple situation which I mentioned before, two poles here, a pole in alpha, a pole in beta. If you have f is 1 over, let's say I use the letter psi here. Psi minus beta, and h is the convolution. The formula which defines the convolution, which anyone here knows, and which was written before, is not ambiguous in the common disk of convergence of the two series. But it's highly ambiguous, that's the point. When you start to circumvent the singularities, the possible singularities which you can meet. And in the questions of coequational resurgence, there are many singularities. Should I do something here for the screen? Okay. Okay. So that's the point. The difficulty lies precisely at this point. There is a formula for, you can solve this equation and by explicit iterated integrals. I will show some of them later on. These iterated integrals are totally unambiguous for psi close to the origin. But then what happens when you start to move and circumvent singularities? Okay, then you have these iterated integrals amount to integrals over simplexes. And these simplexes, we can deform them when we move the variable. And how do we deform that? The method is standard. When you want to deform something, you want to build some isotopies, you take the flow of some suitable vector field. In this context, the method was introduced by FAM in this context once again, and but it was improved by David Sauzin and later enhanced by Shingo Kamimoto and David Sauzin to prove general results of stability with respect to convolution of resurgent algebras. But here we are dealing with more complicated problems. So once again, we have iterated integrals. We define them as explicitly, thanks to the relevant combinatorics, as integrals over simplexes. And we deform the simplexes by some ad hoc vector fields using a technology which was very much developed by David and Shingo. Okay. Okay. Now, and once again, it's very, very packed, but there are many technical steps in this proof. So yeah, I should not erase, no? Let's say, well, I'm sorry about that. Yeah, yeah, I'll turn it once again. Huh. Yes, sorry, thank you, Ricardo. We can do it. Thank you very much. I can finish, thank you. Now, these expansions over words, we can rewrite them as expansion over trees. Why? Remember the ansatz? These design words, and so is some words in letters. In our context, it will be just +1 - 1. And so this guy here is simply, as on the previous slides, composed of ordinary differential operators. They are not alien derivations and nothing here. It's just ordinary differential operators. Now, when you compose, sorry. Yes. Sorry? None of them are getting erased, blue or black. Yeah, I have a blue. Yeah. It's here. Okay. Is it better? We compose ordinary differential operators. Now, there is no alien calculus. The way to deal with the composition of ordinary differential operators is use of trees. Many people in the audience know this. This has been discovered by Cayley in the middle of the 19th century following a question which was asked by Sylvester. And it's relevant to index the composition of ordinary differential operators using trees. That's the reason why Ekal has developed a whole theory on his own called arborification. I have a very short bibliography at the end, so maybe I can show you one place when you can, if you're interested, read about these things. But that's the reason why in this business we index over trees. And in fact, it was technically very important for us because it gave us very suitable, very tractable, iterated integrals on which we were able to prove that they gave rise to this property of endless analytic continuation. Okay, so once again, we have an equation we can index a mold equation, which you have seen before. We have it for Schrödinger equation, for Riccati equation, the same equation, but working on Riccati equation and using trees. And it's natural to use trees because we have a composition of not ordinary differential operators. We find explicit iterated integrals, which enable to reach the first step, which was needed. Okay, so, and in a nutshell, because I have just, I think, 10 minutes, if I'm not mistaken, 12 maybe, okay. We re-expand the expansion for the solution to the normalized Riccati equation. That's why it's the calligraphic Y. It's a sum over trees. And what is this thing here? So a tree is decorated, in our case, with signs. A tree is like that, and it's decorated just by 2 letters. Before we had words with 2 letters. Here we have trees decorated with the 2 letters, -1, +1, which correspond to these, you see, these elementary operators, which were in a slide before. Okay, this way we can define coefficients, which are this time rational numbers, beta t. Remember, before we had the beta plus, which were integers. Here we have to take into account the symmetry factors of the tree. So we have rational numbers, which are explicitly defined, and we have coefficients. The coefficients are these functions at, and they are explicit in the Borel plane. They give us, once again, suitable explicit integrals on which we can prove the property of endless continuability. So one piece of notation here, this thing here is, there is a root here. So if you have a root and you attach, for example, 2 plus, this gives rise to the tree here, epsilon plus plus. That's for the notation, okay? If you have a juxtaposition of 2 letters plus plus, here it just means that you attach the root to these 2 letters. It gives you a tree starting from these 2 summits. So it's important for the recursion relation, which is indicated here. And you see in the middle, you have a mold equation of the same type of what we had seen before. But on the level of trees, for Riccati equations, they are particularly tractable. In fact, the trees we are dealing with are just binary trees, and all their internal nodes, I'll draw an example. Here are pluses, and all the leaves are minuses. So actually the sum which is here is over all these type of trees. And this type of trees give rise to tractable iterated integrals, which I will show now. Okay. And now, so there are some intermediate steps. Of course, it's very packed here. We are led, when solving these small equations of the index by trees, we are led to this expression of this type. So we have integration over some simplex, and simplex is what we call the standard simplex at scale psi. So the definition is here. We take positive numbers, and here it's the zeta v's, v for vertex, for any vertex of the tree here. And we require that the sum is psi. Once again, this formula is unambiguous for psi, psi close to the origin. Okay, and then from this formula, which is once again explicit, we are able to devise explicit vector fields to continue and show that the continuations has only isolated singularities. Okay, so once again to recollect what we have done, we had some complicated functional equations, PDEs in the Borel plane. Instead of dealing with this, we decomposed the solution with this as an infinite sums of functions which are solutions to the mold equations. These mold equations for the Riccati equation, we reindex that by trees. And once again, it's natural in the context of resurgence theory. And when we solve these equations, we find explicit integrals which are tractable and for which we can show that they are indeed analytically continuable with isolated singularities. Okay, check time. Yeah, now this is something, it's not different, it's part of the program, but it's what I had evoked from the start, the thing that was triggered by André Voros' last paper. In the case of a Schrödinger equation with homogeneous potentials, in fact, this question of coequational resurgence, which are more delicate than equational resurgence, can be, in fact, coequational can be rephrased in a problem of equational resurgence by a merging of variables. So it is not always possible, but it is possible for homogeneous potentials. And once again, it was when David Sauzin saw this paper of André Voros that it triggered this calculations of this type. Okay, so you see, we are dealing with a potential here, which is homogeneous. C square is for convenient, the notation. And in fact, the function we consider with a Schrödinger equation, which is written below, and which is homogeneous potential minus the energy, but we rescale the energy. That's the trick. And rescaling the energy using this Liouville coordinate, which in this case is homogeneous also, it's simple monomial, we have to deal with a new Schrödinger equation. At this stage, you don't see much difference, but at least with the next slide, you see that when you merge two variables, meaning that when you consider psi as a function of eta times z, it's a product, it's not eta comma z, it's eta times z, then the function big phi is a solution of a two-dimensional linear differential equation, and there is no eta, there is no Planck constant here. And that's the point. So this function big phi is resurgent at infinity. It has Puiseux series, but it's equational, it's much easier. And so we can, and we have a number already of calculations on this, we can describe explicitly, we have closed form formulas for the Stokes phenomenon. And from that, we can derive relations for the Voros coefficients for the original eta variables. So it is a very particular case. We are on ongoing work on this. It's not the end of the story. Once again, homogeneous potential, we rescale the energy with appropriate constant, and then we merge the variables, and then we have a new second order differential equations with no parameter. Planck constant has disappeared. This has been absorbed in the rescaling of the energy. But the point is that we can go back. Once we know the resurgence properties of this big phi, once again, resurgence for z close to infinity, it's ramified, so solutions are Puiseux series, and we can pull back these resurgence properties to express resurgence of psi with respect to eta. Okay, so in this sense, for this type, this family of equations, equational and coequational are sort of dual. And Ekel has noticed this phenomenon on other types, simpler actually, classes of examples already in the late 1980s. That's why they coined the word coequational. There is some sort of loose duality between equational and coequational. Okay, and my time is almost over. So I will, yeah, I would just, yeah, what I said at the beginning. I don't give the formulas, but I mentioned the bibliography, send you to the relevant papers in a while. So there's these explicit formulas which Ekel found in the 1980s, complicated iterated integrals, but never worked in details the process. Okay, I'll skip that one. Yeah, so as a conclusion, we have achieved the first step. We don't know yet. We have not a complete proof of that the expansions, the Wkb expansions, are indeed resurgent, meaning they are analytically continuable with isolated singularities. This fact, which was stated as conjectural explicitly by André Voros and then by Frederic Famen and the co-workers, but we have achieved the first step. And we aimed, well, we have achieved the first step, but we are quite optimistic for the rest because we have explicit constructions of the vector fields. So we need estimates on these vector fields, but as the constructions is explicit, they seem at hand, but this is not done, okay? Next, we aim to gain a better comprehension of the bridge equations of B2 and B3. There are some, it's outside the scope of my talk, conclude in a minute. There are two bridge equations which are specific of coequational resurgence. And the point is that many areas in recent years, there have been results, sometimes numerical and sometimes analytical, that show features which are typical of coequational resurgence. The coefficients appearing in this so-called bridge equation, which are adapted to coequational resurgence, are rational numbers, even integers. And it's perhaps the case in particular in topological recursion, and I'm happy that we will have a talk in a while about topological recursion. It's a very fascinating subject, the questions of resurgence in topological recursions. Another point which is important for us is that we have a technique to prove a mathematical result, and it can be adapted to other situations. The most natural one is coequational resurgence for difference equations. We can be interested in difference equations with a small parameter, perturbation parameter, and state and hope for results of endless analytic continuations, which seems at hand with the techniques we have developed. And I will conclude by just a few references. Of course, in the bottom is the very famous paper by André Voros, which I mentioned several times, sorry. Was mentioning also the paper by de Labayer and Pham in 1999, where they explicitly stated that to them, the proof of resurgence was not yet, endless analytic continuability was not yet settled. That's why it was worth maybe working on this project. So, yeah, I don't know if this project, the problem will hit us back, but we anyway considered it worthy of attention. Okay, there's the three papers by Ekal. Two of them, one, sorry, is in French, an 84 paper already, in which he dealt with coequational resurgence. Then these complicated integrals I mentioned appeared in 94, but he already had this in the late 80s. And there is a very long paper which appeared in 2020, in which he gives some very valuable information on coequational resurgence. So everything, of course, that Ekal says that's very interesting. On trees, I just mentioned the paper we had published with David and Frederic Menou, where you can see very simply, with no jargon, how these tree expansions enable to solve explicitly a well-known classification problem for which there is no such explicit expansion. So it's classification of one-dimensional germs in the complex field. And two recent papers, well, one by Shingo with expanded resurgent functions for equational resurgence with also tree expansions, published in the Advances of Math very recently. Should appear in a while. The preprint exists for some time. It's not, it should appear, it will appear. The date is written here. And a paper by David Sauzin and then Shingo Kamimoto and David Sauzin about this property of endless analytic continuation. Okay, I think I'm just on time, if I'm not mistaken. So I will stop here, and thank you for your attention.
Question? Maybe let me get the mic.
The mic.
I just wanted to ask a question about the rescaling of the energy. What does that mean to the original energy? Is it infinite energy or close to infinity? You did the change.
Yeah.
The rescaling of the energy such that the
it's just
disappeared, but
it's reverse engineering. I think it's the choices are made in order that in the end, when we merge the variable, we don't have the Planck constant anymore. We don't have the eta variable.
I understand that for the rescaled energy, you can then fix whatever. But I'm saying that means that the rescaling did something to the original energy. The original energy depends on the h bar or the eta parameter, right?
Yes.
So does it mean that we're taking a regime where it's small energy or large energy or anything?
We have not discussed that, and in fact, I'm not proficient to discuss that. I see the point of your question, but it's just at this stage a way of going to equational to coequational. Then we have explicit formulas. I guess that some answers can be given to what you are asking thanks to these explicit formulas which we obtained. But and once again, it's very recent, so no, I'm not. I don't think I will have any sensible thing to add to this. But thank you.
All right, just a quick question. Do you have simple examples of ODEs that are not endlessly continuable?
Well, you can you can put in the data of your ODEs function among the coefficients, for example, a function which has a barrier of singularities. This is sort of an you see a function which is analytic in the unit disk, but with a barrier of singularities in the unit disk, in the Unix circle. But it's sort of an artificial example. And beside that, Ekal's theory has extensions to quasi-analytic continuations. It's a part of his theory that is very complicated. For now, no one has really, up to my knowledge, gone into this. But it's possible to go beyond isolated singularities. I can give you the reference for that in Ekal.
Anything else?
Sorry, no, I just saw a hand raised by Boris.
Yeah, I was gonna go to that.
So if there's nothing else in the room, Andre, if you want to say something, go ahead. No, I guess not.
Then let's thank Frederic once again.
I have a question about the original definition of Ekal. So in this talk, you concentrate on the endless continuity.
Yes, only that.
But you mentioned that if you find a new function around some singularity, this must belong to the family. Now, is this family a finite set of functions, or it is characterized in some way? Because otherwise, you can say that when you find a function, you say welcome in the family.
I see your function. Yeah, I see your question. Thank you. Let's see. If I manage, yeah, it should be enough.
Let's have a quick answer because we're really late.
Yeah. Okay, let's say, then maybe I will not try. If you have a linear equation and you're interested in, just like in the very end here, okay. The last one. Okay, see, an equation of this type, you have equational resurgence. So it means that you have a basis, a vector space of solution. You have two functions, big phi 1, big phi 2. There will be resurgent with respect to the variable z, which will be a ramified once again in this example at infinity. So in the Borel plane, you see, in fact, in this case, for this linear two-dimensional differential equation, equational resurgence, a ping pong. There will be one singularity in the Borel plane for phi 1. Once again, two elements of a basis of solutions. Phi 1 will have one singularity, and in the singularity of this single singularity of phi 1, you will find phi 2. So the family here is just two functions, okay, the basis of solution. But if you have a non-linear, even very simple one, like x squared d over dx f equal a function of x and y, non-linear, you have trans-series solution, this infinite sums of exponential here of 1 of n over x times phi n. So you have an innumerable family of functions, all of which have resurgence, and the resurgence relations interconnect in all these components. So it's not some vague notion of families. It's you have a space of solution which is formal space, a space of formal solutions. It has components which have series. All these series are resurgent, and the resurgent relations are expressed between all these components. Is that an answer to? Yeah, we can discuss later.
All right, very good.
Thank you.
Yes, comment?
Let's move on to the next speaker.